Good afternoon. I'm Owen Gorman with the Great Lakes Science Center. Apologize that I could not be more virtual with you today, so I'm going to present for you a pre-recorded presentation. I've been working with Tim Johnson and Aaron Fisk and Kevin Loftus and Roger Gordon in addressing this question of, is barotrauma a factor in the survival of stock bloater? Before I get to the question of the effect of barotrauma on bloater, we need to review the stocking strategy of bloater in Lake Ontario. Young bloater are stocked as juveniles, fall fingerlings, 100 millimeters in size, and fall yearlings, 150 to 170 millimeters in size. They are stocked during the daytime, and they're stocked over deep water, 50 to 100 meters in depth. It is assumed that this approach reduces predation mortality, and it's the same approach that has been used for stocking yearling lake trout for decades. Acoustics show that the fish swim downward to the lake bottom after release, reaching 100 meters in 7 minutes. The fish appear to pause at approximately 30 to 50 meters in depth and then continue on to the lake bottom. As I look at this echo view plot, as a bloater being released from the surface, it reminds me of rainfall. These acoustic tracks show that the bloater move continuously to the lake bottom, although there is some pausing at the 30 to 50 meter depth. So far, more than 1 million bloater have been stocked into Lake Ontario since 2012. So I guess we could say at this point, all looks well. Now, I've had people ask me this question as to why do these fish swim downward to the lake bottom? They've only ever been in very shallow water. And why would these fish swim downward if it might cause them harm? So this reminded me of a little song from the movie Finding Nemo, and some of you may be familiar with it. And in this instance, it is Nemo's dad, Marlin, is discussing with Dory as to whether they should swim into the abyss.
Hey, Mr. Grumpy Gills. When life gets you down, you know what you gotta do?
I don't want to know what you gotta do.
Just keep swimming, just keep swimming, just keep swimming, swimming, swimming. What do? We swim, swim.
Dory, no singing.
Oh,
Dory.
I love to swim in.
Dory.
When you want to swim, you want
See,
to
I'm gonna
keep
get stuck now with that song. Now it's in my head.
Sorry.
At this point, I want to summarize what we know about the fate of stock bloater. Hatchery-reared bloater have only experienced a maximum of 0.1 atmospheres of pressure in the hatchery. They are stocked during daytime over deep water, 50 to 100 meters depth. They swim rapidly to the lake bottom, achieving 5 to 10 atmospheres of pressure in as little as 4 to 7 minutes. Tag bloater show high predation, approximately 60%, and high short-term mortality, approximately 40%. More than half of the fish that are not predated die within 24 hours. So could these fish be suffering from compression barotrauma? Now, decompression barotrauma is widely recognized as a cause of death of fish. That is when we bring fish up from depth too quickly. But compression barotrauma is undocumented in fish. There are simply no published articles on this subject to be found. So no one believes that this could be an issue. And so finding funding has been challenging. In early 2020, the Great Lakes Fishery Commission provided $2,000 to fund travel to the Jordan River National Fish Hatchery to investigate the possibility that compression barotrauma could cause rapid morbidity and mortality in hatchery-reared bloater. But then the question comes, since this was in 2020, when are we going to be able to go to the hatchery to do this research? Well, we got our opportunity in November of 2020, and we gathered up our equipment and made a road trip to the Jordan River National Fish Hatchery. So what did we do? We have this hyperbaric apparatus for fish. We call it the HAF. This device was used to simulate the bloater diving to the lake bottom. We conducted 4 trials with adult bloater, and each trial took an entire day. The first 2 were rapid compression to 2 different depths, 50 or 70 meters depth, And so we've got these fish down to depth in approximately 5 minutes or so to basically simulate what has been observed in the field. The second one was a slow 3-hour compression, taking 3 hours to reach the equivalent of 50 meters depth. And the fourth trial was the standard rapid compression to 50 meters of depth and holding these fish there for 3 hours. All fish were slowly decompressed for 3 hours or more. Each trial had a paired control, and more than 5 hours of video was recorded of fish behavior during these trials. The dead fish were dissected to inspect internal organs and to look for any signs of hemorrhaging, and the surviving fish were held for 30 days for observation. So here I present a montage of pictures of our work at the hatchery. We set up our portable laboratory next to the raceways inside one of the massive hatchery buildings, which we found tended to drop snowflakes on us during the morning hours. We took our fish from a next raceway where there are adult bloater for our use in these experiments. Each of the pressure tanks has a console with a live video feed, which you see here in the lower right. And there's also instruments at each one of these half units that monitors temperature, pressure, oxygen levels, which is logged on regular intervals. The fish are illuminated inside these tanks with infrared light. And of course, there's the control system, valves and levers galore to control the pressure within each of these vessels that we're doing our experiments with. So what did we find out? Bloater exhibited acute stress when compressed. Stress was evident at pressures as little as a half an atmosphere. That's the equivalent of 5 meters of depth. And we could see this within minutes of the very first trial. Moderate stress is indicated by increased respiration and activity, swimming speed, etc. Acute stress is indicated by disequilibrium and lying motionless on the bottom, or on their side, or upside down. 44% of the fish reached this state in the compression trials. Decompression alleviated the symptoms of stress caused by compression. After the trials, of the fish that were compressed, 19% of the fish died within 48 hours, and those mortalities increased to 25% within 7 days. 6 of 7 of those mortalities had ruptured swim bladders, and that provides evidence of compression barotrauma. No control fish died. So in conclusion, we found evidence that compression barotrauma causes morbidity and mortality in hatchery-reared bloater. So I'm going to just show you a short video clip of what these fish look like inside these pressure vessels. On the left are the fish under compression under the equivalent of 50 meters of depth. In the control are fish that are at sea level, essentially no pressure at all. And you will notice a rather big difference in their behavior. So what you see on the compression side, you see a lot of particles being stirred up, flotsam in the water, caused by a lot of the fish movement. There's 2 fish lying on the bottom. And whereas you look on the control side, these fish are just gently gliding back and forth through the screen in view. So the implications of our research thus far is that compression barotrauma may affect fish stocked over deep water. And this has implications for current stocking practices. They may need to change. And this is all pertinent because there is interest in restoring kai, a deepwater cisco, into Lake Ontario. We still have a lot of work to do on this project, a lot of fish to dissect and look at, analyze a lot of video footage, etc. To better understand what we have at hand right now. But we also want to be able to look at the effects of compression barotrauma on sizes of bloater that are typically stocked in Lake Ontario, and that would be fingerlings and yearlings. To that end, we brought 500 baby bloater back to our station in Ashland, Wisconsin. So to support this, we are looking for additional funding, and there is interest in expanding the scope of the study to include Cisco and lake trout. And all of this may provide a guidance for improved stocking methods to reduce the likelihood of barotrauma in efforts to restore bloater and other species in Lake Ontario. So this research is really in its starting phases, and it will be continued. So in closing, I wish to acknowledge the collaborators in this study and those that have made contributions, and to the Great Lakes Fishery Commission and U.S. Geological Survey for their funding of this research. Thank you for listening.